Hello, everyone. Welcome back from the break. Igor Sokolov will take us through a talk entitled The Microcanonical and Finite Temperature Ab Initio Molecular Dynamics Simulations on Quantum Computers. Take it away, Igor.
Thanks a lot. So I will start by talking to you about how do we simulate dynamics on
Hello,
quantum.
everyone. Welcome back from the break. Igor Sokolov will take us through a talk entitled The Microcanonical and Finite Temperature Ab Initio Molecular Dynamics Simulations on Quantum Computers. Take it away.
Sorry, I'm back in a second, I think. Voila, sorry, I had YouTube on. So yeah, so let's start. My talk is going to tell you how do we simulate chemical systems and their dynamics on quantum computers. So I'm a PhD student at IBM Rushlikon in a team of Ivano Tavernelli. And here, the message of my talk will be the following. So we want to show that we can nowadays simulate small molecular systems, and this in running the dynamics in a constant energy and temperature ensembles. And this we will need to use Hellman-Feynman forces to do that. And this is important now because so far not many studies have performed the study of trajectories and how the noise of quantum devices would affect dynamic simulations. So I will first start with a method. This method will, of course, require the calculation of forces, and these forces will have noise. So we would need a mitigation technique, which Panagiotis Barkoutsos introduced to you before, Langevin mitigation scheme. I will show you the results. And this mitigation scheme will be very important for geometry optimization to obtain the correct structures. Then we can go further and do the dynamics in microcanonical ensemble. And then we need to preserve the total energy. That will be our goal. And we will see how noise will affect this. But also we will show how we can do Langevin dynamics, meaning that we need to now preserve the temperature and we can take advantage of the noisy forces. Finally, I will conclude this talk. So let's start with the methods. And our method is simple. So we used the variational quantum eigensolver, which you already heard the detailed explanation from many talks. I will make a short summary for you. We have a selection of a system. In my work, we did the hydrogen molecule and the H3 molecule, H3 plus molecule. So we start by using a classical driver, such as, for instance, PySCF, which would run a Hartree-Fock calculation and compute the integrals. This, in turn, will allow us to write the Pauli strings which correspond to our Hamiltonian and would allow us to measure the energy of the system. And this we can use with parity mapping or Jordan-Wigner. In our case, we have employed the parity mapping because we can profit of the symmetries present due to this mapping using 2-qubit reduction, which takes out 2 qubits from the system, allowing us to obtain faster the results. So therefore, for instance, for H2 molecule, we would not have 4 qubits, but 2 qubits. And in case of H3 plus molecule, we employed additional techniques, which are the restricted Hartree-Fock formalism, which allows us to employ half the amount of qubits. So we lose the notion of spin up and spin down electrons, and therefore we don't double number of qubits, but we have half them. And this, for H3 plus, we would need, for instance, 6 qubits, but then now we can run on 3 qubits. And then we can additionally use the tapering off to taper off extra qubits, so we have 2 qubits problem. Therefore, we can do H2 and H3 plus on 2 qubits in this work. Having our Pauli strings for both systems, we can then prepare an initial state of a quantum computer. And you have watched many presentations today which tell you very sophisticated methods unitary coupled cluster and its variants, also Ry and Z swap RZ, etc. And this is can work with my methods, but we try to keep it to the minimum. We employ the simplest ansatz, actually, the Ry ansatz in our case. And you can see a scheme here of the 5 qubits we used in our work with qubit 2, qubit 3 of Athens chip, IBM chip. And then having basically the energy, the measurements of the Pauli strings, and then we can also compute the forces, the force operators with two methods, finite differences and Hellman-Feynman, which I'll go into details later. And all these observables can be used with noise mitigation schemes such as Langevin. And then we have a choice of which equation of motion we integrate, our Newton equation of motion or the Langevin one, depending if we want to conserve the energy or conserve the temperature. And this in the VQE, of course, we repeat this procedure every time we change the geometry with equation of motion. By computing the accelerations here, we would need to recompute the Pauli strings, recompute the ground state, and iterate in a loop like this. So this is our methods. And you see we need the forces. So now I would like to show you the simplest method we can think of is the finite differences. Finite differences are not employable in this case. As a starting point, I will tell you why. Basically, you can see immediately that we have to compute psi plus and psi minus. These are the ground state wave function at displaced geometry along Cartesian coordinate for each nuclei I and direction alpha. So this means two displacements for three axes and every nuclei. So we need to perform 6 n VQEs to compute the forces. This is a large amount. Therefore, we need a different approach, and Hellman-Feynman theorem is applicable. We will show why. And here we just need to compute, you see now the differences of the values of one-body integrals and two-body integrals. And we keep the expectation value of our hopping terms, one-body and two-body terms, at the initial geometry R0. So with the VQE, we compute a ground state. We have the Pauli strings, and then you can see in Hellman-Feynman forces, we need the same Pauli strings just with different prefactors given by these differences here and here. So we can reuse basically the already measured Pauli strings to compute the forces, and this with only one electronic structure calculation such as VQE. So it is extremely good method, but we need to be sure that we can apply it because we have the contribution of the wave function to the forces. When we do a derivative of our energy, we apply derivative also on psi here and here. And these contributions in some cases are rather large when, for instance, when you're at the limit, of course, an infinite basis set, then the Hellman-Feynman theorem holds. But here we are in a minimum basis set. We will do simulation everywhere in STO3G basis set. Therefore, we need to be sure that this will be working. So we did here a calculation. For instance, you can see on subplot A, we did the potential energy surface by stretching the bond of the hydrogen molecule. This is calculation in cyan is done with exact eigensolver. And then what we did was to do a simulation of our classical algorithm called MR using Hellman-Feynman forces. So all these circuit gates are computed using matrices. There is no noise. So this simulation is exact. But it uses Hellman-Feynman, and exact does not use Hellman-Feynman here. To use finite differences, we have very precise forces, and you can see they correspond. But now we need to make we need to show what is the difference actually within exact forces, which are these computed with exact eigensolver, and the ones computed with Hellman-Feynman theorem. which we show in example C here. You see that at optimum bond length, we have the worst error. So it means the Poulet contribution is only 0.4% of the force. So the Poulet terms are very negligible in this case and can be ignored. Therefore, we can apply this Hellman-Feynman theorem and the forces. Then I want now to show how can we basically take out the noise from these noisy forces. And then we have basic types of noise, which we model in Qiskit. Therefore, the gate errors, we model thermalization errors and readout errors. And this can be seen as you have your noiseless density matrix summed with your density matrix, which has errors in it, with a prefactor f, which can be from 0 to 1. And this can be expressed also as a sum with a cross operator, like this. So then it renders a valid density matrix. So these, of course, are not all type of noises, but the ones which we are using to model our chip, which is this IBM-Q Athens chip. And you can see here that how we implement the denoising routine. We have our noise density matrix on which we apply Hamiltonian minus D. This morning was explained. I will repeat it quickly to remind you. We have our noiseless density matrix. So you can see the ground state and the excited states. The ground state had major contribution. As soon as we have noise, we have a large contribution from the excited states. And then we can apply sun, which basically our noisy density matrix, which H minus D, and D assumed to be identity matrix, multiplying an identity matrix. And we can renorm it, basically. And this renormalization then allows us to suppress the contribution of the excited states. So basically, you see that we have to multiply our operator, which could be force in our case, and observable. And we need, therefore, to square the Hamiltonian. And the scaling, you see that we have, of course, this it cost us to measure additional terms. And this is how it scales with NH be number of Pauli strings in our Hamiltonian squared times the number of Pauli strings in our operator, which we try to measure. So this is the cost we have to pay with this approach. Next, we tried in practical sense to find the value of this parameter D. So for each different basically distance, bond length in our H2 molecule, we computed what is the error on the energies and the variance on the energies. And you can see that basically at some point, if you put your D value too low, you have significant variance and significant errors. So actually, we need to choose somewhere around this area, our parameter D, for our simulations. And this value, actually, there is a nice rule of thumb, because you might think, what do we have to do with this study for every case? Actually, we just have to be, this value of D has to be around the Hartree-Fock energy, but it's just a heuristic which we used. And this renders us good results. So I will show you how to improve the results. For instance, let's take the case of the geometry optimization. We run it on our H2 molecule with minimal basis set, Cobila optimizer with VQE, and on 2 qubits because of 2-qubit reduction and parity mapping. 8,000 shots and our RY circuit. So you can see we have just a single CNOT and we have only 4 parameters. So as soon as we run the calculation, we can see here MR basically is a column which gives us the bonds for these 2 molecules, H2 and H3 plus, basically give us the exact values. And then we have our VQE, which has full noise model with all previous 3 types of noises included. And we have deviations, large deviations from what we want to obtain. And as soon as we employ Langevin's mitigation scale on the top, we are significantly close. So you can see 2 milliangstrom close for the bond length. So the Langevin scheme definitely improved the quality of forces in this case. And just to mention, I forgot to mention here, we have employed a very simple steepest descent algorithm going in the direction of the gradient to minimize this geometry. So Langevin's algorithm shows promises, and we can try to use it for microcanonical molecular dynamics simulations. Let's see what the results are. So let's start with what happens when we have all the noise sources active. Here I show you the results of 100 femtosecond simulation, its potential energy surface. And I show you here the basically the state vector result, which this SV means state vector, which is also the exact solution basically of our problem using exact forces. So you can see that we have a big gap, and also the optimum bond length, the minimum of this well has shifted. So, but you can see having this huge error, we are not at all in chemical accuracy here. We still have the forces which are somewhat decent. Of course, here we have very bad area, but it is not, the forces are quite robust basically to noise. So we can still obtain some dynamics here. And now we have to show how can we improve it. So we can improve it using Langevin's methods. And you can see that doing the same dynamics, employing Langevin's mitigation scheme, we have suppressed here the gap in potential energy surface. We are very close to the exact result. In terms of forces here, you can see the forces are now very accurate here. And this shows here in the subplot C, where you can see that the difference between the exact forces and the forces computed with Langevin's scheme, we have basically very low errors in order of 10 power minus 5. So this scheme shows promises now, and I want to show you what happens with potential kinetic and total energy of the system during these runs. Here we have no error again, no error mitigation. I mean, we have all the noise sources of IBM-Q chip, and you see the total energy is overshot here, and then it diminishes. The most drastic effect of the noise of our chip is here, where we see that the kinetic energy diminishes. It means we have large errors on the forces, and also we have certain dephasing here. So we thought we can think what would happen when we manage to halve the device noise now. So if we halve the device noise, we would have substantially better dynamics. We can see here the total energy is better conserved. It's reducing, but it has a revival here somehow. And especially the kinetic energy is now conserved. We have substantially less loss of it. But as we cannot, when we run it on a real device, we cannot reduce the noise. We have to employ some methods and to see what is the source of this. And first is the shot noise. Maybe we're not using enough shots, enough measurements. Shot means how many times we measure each Pauli strings or the operators, the force operators, basically. Here we had 8,000 shots. And here we have 81,000 shots. And we can see that the variance of the total energy has diminished, but we still have the decay. And we still have the decay and the kinetic energy here, but also significant, quite less so. So this is not the source of our problem. So it's not the shot noise which poses the problem, is the other 3 types of noise sources which are responsible for this. And you, of course, as we have the noise of the device, this is, of course, this is all done on the emulator, so we can triple it or diminish how we want. Here we halved it, and we obtained rather good conservation of energy, and everything looks rather well. but we need to do it right now on our device. So let's see and employ our Lange's mitigation scheme. And basically, as you can see now, with Lange's mitigation scheme, the total energy is rather conserved. And similarly for the kinetic energy, as in the case we've just seen on previous slide for the half noise with a larger number of shots. So Lange's mitigation schemes works for this problem. And of course, the half noise result is as good as, although maybe here we have a little bit, it looks slightly worse, but this is due to the number of shots used. So later, we wanted to, of course, run it on a real device. And here on the left, I put you as before, what happens when we don't have Lange's mitigation scheme. We have decay in total energy, decay on kinetic energy. And when we run this, not on the emulator now, but on real device, here is what you observe. We have a quite rather good conservation of total energy. And also in terms of kinetic energy, we sort of lose a little bit, but we recover here. So this seems to be, this 20 femtosecond of the simulation seems to be in agreement here with what we see in our simulation with our emulator. But it really, in potential energy, it looks significantly better here. So we obviously could run this for longer duration. We were just limited in our resources allowed for us to use on this device. And next, I want to show you what is actually the influence of the individual noise types. These three noise types, one is the depolarization error. And you can see that if we just include this error without the readout error and thermalization error, we would lose a lot the total energy, and also the kinetic energy is reduced drastically. If we have only the thermalization error now, we are significantly better in kinetic energy, and we also have certain revival of the potential energy. But still, the polarization error remains the main source of our problem. Also, the readout error, if we do not employ the readout mitigation, which Panos had explained you this morning, uses a calibration matrix to mimic this, to reduce the error. Here, basically, we have this large gap in the total energy. We previously seen, then when we don't employ any mitigation, we have this enormous gap, and we're not in chemical accuracy. And you can see below that still the forces and so on, because it can be seen through kinetic energy that the forces are fine, are quite okay, because here we have still kinetic energy is somewhat conserved. It does not diminish too much over the duration of 150 seconds. So depolarization error is the main source of our problem. That is the outcome of this study. And then we've just seen everything to do when we want to conserve the energy in our simulation. Now we can also think that we can take advantage of the noise in our forces. And this is in Langevin dynamics. We want to conserve the temperature. How do we do it? So we've seen that we first tried to in Microcanonical ensemble to integrate equation of Newtonian equation of motion using the Verlet algorithm. And we've seen that we with Langevin can obtain rather great results. Then now we just have to switch basically in our code the equation of motion, which now includes additional terms, which are the friction term, this gamma r, and this Gaussian white noise force eta t. And the important point, this noise, it has so average equal to 0. And we can relate this friction actually to our noise in the forces through the covariance matrix of the forces. So in this way, we can use the statistical noise of our device to drive our dynamics. And of course, we need to check that this assumption we can use the noise in the forces to drive the noise has to be checked and verified. So for this, we did the following study. First, you can see here, just in the case of microcanonical dynamics, if we produce a phase space plot, what we obtain, when we do a Verlet with MR means our exact solution. So we have just a ring here going around, means we conserve the energy. Then if we employ a Langevin mitigation scheme, we remain somewhat close in sign going around also. But as soon as we do not employ any mitigation scheme, we lose the energy. And therefore you can see the decay towards the middle and we have less and less energy. The characteristic distribution of bond length associated with this kind of dynamics is this bimodal. So the molecule remains at the most close when atoms are very close together or furthest apart. Here you can see that's the molecule remains the most ideally. And we will contrast this now with Langevin dynamics. In Langevin dynamics, the phase space, so the momentum here and the bond length basically of our H2 molecule looks very different. You can see here that we have a very different distribution of bond length. And one way to verify that we do correctly the dynamics is to see that this distribution has to follow this Boltzmann distribution like this. H would be our harmonic oscillator basically, and we would do a fit here of harmonic potential inserting here. With this fit, we can then extract the beta value and compute the temperature. And this temperature of our system should be in agreement with the one computing using the kinetic energy. And so if these two values are close to each other within certain error, then we are sure to sample collect correctly the Boltzmann distribution and doing everything right. So we indeed had an agreement in calculating in these two ways. We obtained for this simulation, we obtained 120 Kelvin and with uncertainty of 100 Kelvin, which computed the binning technique. Otherwise, the uncertainty is extremely low. That's why we need to use binning. This, you have the parameters here. So having this, we now arrive at the conclusion of my talk, actually. So we have seen that we can use Hellman-Feynman forces in combination with Langevin's noise mitigation scheme to provide accurate forces that allow for longer simulations. But we have seen that we have additional costs due to this Langevin mitigation scheme, which is n power 2 of the number of terms of the Hamiltonian, and times also the number of terms in our observable, such as force operator. Then we've seen that we can use effectively the statistical noise to drive the dynamics in a constant temperature ensemble. And of course, our plan is to make this code, which can do all of this, available in QCxQC in future. So QCxQC is the software we use to run all the simulations, of course. So with this, I would like to thank a lot to all my team, especially Ivano, who led me on this quest, and of course, especially to you for your attention. Thanks a lot, and please, do you have any questions?
Thank you very much, Igor. Very, very nice talk. Thank you. Going to the Slack now. Yes, stimulated a few questions. Yeah. First question by Bruno Sengen. Is there a physical reason for which the parameter D can be taken as the Hartree-Fock energy? Or is it just an observation from different numerics?
Yeah, exactly. That was just, it's completely heuristic. So we tried many different systems and it worked for us. So physically, I cannot give any like mathematical why it works so well. So for this, I think would be better. There is this work by my colleague Philippe. So I gave the link before, and he gives extremely detailed explanation of many reasons of the choice. So probably it's better to refer to this paper here. I will highlight it here at the bottom. Yeah.
Oh, I see. Great.
So yeah.
Sorry, do you have more?
Yeah, no, this is it for
Okay.
If it's satisfactory.
yeah, that's I think that's fine. Yeah, thank you very much. Next question by Falgun Lolor. Good talk. Can you explain your reasoning for using Kobila instead of SPSA on your 5-qubit device? Or as the case may be, if you're using it on the 5-qubit noise model in your Kazan simulator?
Yeah, so we use the Kobila optimizer. So basically, I basically tried a whole range of different optimizers. And from this whole range, but basically what we have available in Qiskit for this particular circuit and the problem, this work extremely well. And if you go to larger system, perhaps it will work better. But for instance, with Kobila optimizer, in 50 steps of VQE, I could obtain already ground state energy. With SPSA, I would need 2000, even more. So in this particular case, I'm saying it works the best, but I'm not sure it can be worked for any other larger system that well.
I'm not familiar too much with SPSA. I know Kobila is gradient-free optimizer. Is that true of SPSA as well?
So SPSA, it's so the way it computes, it always goes in stochastic direction, yes, and it always shrinks gradually the step. And it just always, the gradient is always stochastic, direction is always random. In this way it works, and it just shrinks its step, and eventually it arrives at the minimum in this way. It's very simple.
I see. Yeah. So those search vectors are obtained without gradients, if I understand.
Yeah. Internally it computes, it's a stochastic gradient. Yeah, it computes away certain.
Okay, next question by Sydney Ramos Santana. Are there any computational barriers to implementation and computing properties with other ensembles, such as canonical NBT or isothermic isobaric NPT? Are there challenges to do that?
Thank you. We have not actually explored, but I don't think there is any barriers. We just have not explored it yet. Probably will be a work of future work.
Great. Yeah. And one more question by David Jolt-Manrique. What would be the relation between the number of shots and the effective temperature of the system?
Yes, exactly. So with large number of shots, so far, so this should not actually be, so with less number of shots, we have a higher temperature so far, and with less number of shots, we have a lower temperature. This is how so far it worked for us. Yeah.
Interesting. Okay. So I don't see any more questions from the Slack channel. I was wondering something probably pretty basic myself. I'm not 100%, I'm not very familiar with ab initio molecular dynamics. But I was wondering, so at the start of the talk, you mentioned that you rely on restricted Hartree Fock in order to reduce basically half the number of qubits compared to explicitly including spin functions. Number one, is it different? I guess it's not very, at least theoretically, difficult to extend that to non-RHF to explicitly include alpha and beta spin functions. But then when you do that, also a few slides later after you mentioned RHF, that you mentioned that the Poulet forces due to the finite size of the basis set was acceptably small. Does that Poulet error come into play more significantly if you start including spin functions? If you have basically a larger a finite basis set, do Poulet forces start becoming more important there? Would you think, or would it still not be too important?
So I do think for this problem would not matter, but maybe for larger systems where you would Poulet forces really need to have large basis set to apply Feynman-Feynman, not to have this. So I think for larger system would maybe be a problem at some point, but for this small system we're currently stuck with now because of our because of limited circuits we can put on our devices, I think this is not a problem.
I see. Just a small follow-up on that as well, which is, it might be difficult to answer, but I'm just wondering if you have any feel for it, that if in the case where you do have to, where the Poulet forces are appreciable and you have to consider them, does the extra terms in your equation you have to include to avoid the Poulet forces, does that add, how much overhead would that add to your algorithm?
Yeah, I mean, this derivative of the wave function, I've found works that actually tell you how to compute them. And there is a way by having an extra ancilla to compute them. So that would mean run addition measurements. So I guess we'd need for the two Poulet terms, this for left side of the expectation on the right-hand side. So I think double number of measurements at least there.
I see.
So I would guess but this is only a feeling, because we don't think so far to implement them.
I see.
Rather small.
So likely just a double of the number of measurements.
Yeah, I would purely on a feeling.
Okay. That's fair enough.
Yeah.
Okay, thanks very much, Igor. I see no more questions on the Slack channel. So I think we can leave it there and everyone can go over to Oina Mete's talk.
Yeah, thanks a lot.
Thanks very much, Igor.